welcome to this Switch On Skills webinar on the introduction to low carbon active buildings. My name is Dr Nathan Cooze and I'm working with at Swansea University. I've got a background in materials engineering. And one of my first projects actually was building integrated photovoltaics back in a long time ago, actually, in my undergraduate project. So it's quite nice to come back into this topic, and I've learned a lot whilst making this course. Okay, so let's make a start. So like I said, this taster session covers active buildings, and we're particularly interested today in low carbon active buildings and what that entails. As we're probably very aware of, due to climate change, and these days it's a climate emergency, renewable, cleaner and more sustainable renewable energy technologies are replacing more traditional fuels like coal, natural gas, and oil in order to generate energy. Where low carbon active buildings come in, these further support the wider grid network by intelligently integrating these renewable energy technologies for heat, power, and transport. And these buildings particularly have a focus on reducing carbon emissions, both during their construction and day-to-day operation. This is the course program of the full 10 credit course, which is currently in development. And what we'll do is, I'm not going to go through them now, but we firstly cover renewables and energy generation. And then before going on to defining active buildings and some of the principles that are important during the design and construction of these active buildings. And we also discuss the impact and regulations as well. But today I'm just going to present an overview of some of these topics, just to give you an idea of what the course entails. So why is this topic important, and why is it important now? So like I mentioned, climate change or climate emergency. We often think about human-induced climate change as something that will happen in the future. In reality, it's an ongoing process, and there is actually a climate emergency now. The ecosystems and communities around the world are being impacted today. We can see some images there, and obviously the news has been full of the wildfires that are happening in the US at the moment as well. So the climate change is here, these findings from July 2023 to June 2024, global temperatures were the highest on record, and we keep sort of breaking these records of global temperatures. This created a year-long stretch in which Earth was 1.64 degrees hotter than in pre-industrial times. So we use the pre-industrial times, 1850 to 1900 as the benchmark. The aim, which the world has agreed, so COP meetings, they've agreed that we should stop the planet heating by 1.5 degrees Celsius. So, last year we already were greater than that, so 1.64. It doesn't mean that we've failed that target, because the target is actually measured over decades, averages rather than single years. But it's still, it's still quite a shocking figure, and it's not a good sign of how things are going. I wanted to show you this short video. It's from 2018 actually, for the UN chief, and he warns of an existential threat to humanity. And I thought it was very relevant, obviously, at the time, but even more so now.
Every day, I'm faced with the challenges of our troubled and complex world. But none of them loom so large as climate change. If we fail to meet the challenge, all our other challenges will just become greater and threaten to swallow us. Climate change is quite simply an existential threat for most life on the planet including and especially the life of humankind. The Stone Age did not end because the world ran out of stones. We do not need to wait for coal and oil to run out to end the age of fossil fuels.
So yeah, some stark words there. What all we can do really is work towards trying to slow that down. I don't think it's going to be a long time until we may not be able to prevent it ever. We're just going to have to try and mitigate those scenarios. So I wanted to bring this slide up just to make you aware really of government policies and regulations. There are a wide range of different policies and different target dates and things like that. And as soon as I made this slide, as soon as we made this slide, the regulations, the dates are changed. So it becomes out of date very soon. The important thing is that that we check up to date figures and targets and from trusted sources. So just to go through this briefly, the IPCC had predicted that we have until 2030 to limit the global temperature rise to 1.5 degrees. So therefore, this need for solutions is happening now, and hence why there is such focus and urgency on climate change and net zero. So if we start here at the bold green arrow, which is coming to the end of 2024, we can see that in November, the COP29 took place, conference, where existing targets were reviewed. And it did in the end, it did result in an improved outcome on the finance target, triple the previous agreement for the most vulnerable development countries by 2035. It nearly didn't end that way, and they did get an agreement of sorts in the end. So already those sorts of figures are changed from the last COP conference. Next, we can see the Future Homes Standard, and in particular Part L, which is relevant for Wales. These have indicated that there will be no new gas installations in new homes from 2025. And in fact, there was meant to be a ban. There was initially a ban on gas boilers by 2035. Just last week, this was scrapped, and now the government are going to encourage a switch to low carbon options. So, even as close as last week, this the slide has changed and will need to be updated. So just to make you aware of that, really, there's many other policies and targets which have come out, like the RIBA 2030 climate change to help architects design within a climate conscious trajectory. And other things then, like obviously the Climate Change Act and also the Paris Agreement. These regularly change dates, and they also have different targets for 2030 and 2035, but they do eventually aim to be climate neutral at the end of the date sort of time bar there, to an economy with net zero greenhouse gases emissions by 2050. Sorry. So yeah, just to highlight again that there are many more targets and initiatives which aren't on this slide. And it's just to give an overview, highlighting some of the building relevant ones, and just to keep up to date really with the latest information and guidance, because it does change a lot. To end this section on climate change, before we go on to active buildings, I would like to finish up with this cartoon by Pulitzer Prize winning cartoonist Joel Pratt. It's from 2009, but you can just see how slow change is to be implemented. And we are making changes, we are making progress, but the overall sort of climate change, climate emergency is still going on, and we do need to tackle it. So the cartoon shows a conference presentation slide and the benefits of climate action, as in the blue there, like energy independence, preserve rainforests, sustainability, renewable energies, technologies, and clean air and healthy children, etc. for the future. And then a question coming from the audience: what if it's a big hoax and we create a better world for nothing? So yeah, you can see that even though it's over 10 years old, the cartoon is just as relevant today, if not more so. And it highlights a range of positive benefits. There's a lot of debate about climate change, but regardless of that debate, arguably all of these that are listed here are positive benefits for taking the action on climate change anyway. So why don't we just do it? Just to cover briefly carbon emissions. This is a slide showing an analogy of that. It can be seen as a huge pile of bricks, and every day you add more bricks onto the pile, and the pile gets bigger. And that's the same in terms of emissions as well. Doesn't matter if you slow down the addition of these bricks, the pile will still get bigger over time. So we do need to start removing bricks and therefore carbon emissions from the atmosphere as well. So as well as minimizing our carbon emissions, there's also ways. So this is covering positive emissions like shipping and aviation, where going away from any carbon emissions is going to possibly be impossible. Probably be impossible. Whereas we can actually have some negative emissions to offset, so it's called offsetting, like things like land management, where some carbon will sequester, but we can also capture some of this carbon and store it underground, as well as other methods like bioenergy with carbon capture and storage. So BECCS there, and other methods like direct air carbon capture and storage, or the DACCS. So there are ways that we can try and capture this carbon and offset our sort of emissions, which we might not be able to get rid of. But important thing is, the less carbon we can use in the first instance, then the easier achieving net zero should become. So that brings us on to the built environment and the role that it plays in net zero. It's not just things like fossil fuel plants, power plants, or the aviation and shipping industries, which we think of are, the big carbon dioxide emitters. Think about, there's so many buildings in the world that globally, these buildings in operation are responsible for approximately 40% of energy consumption and 28% of carbon emissions. If we can design and construct low carbon active buildings, this presents a major opportunity for reducing greenhouse gas emissions and carbon emissions, and helping to protect the environment for future generations. Thus, there is a need for low carbon solutions. So brings us on to low carbon buildings. I'm going to show you a short video of an overview of low carbon active buildings. This was made by Swansea University, and it's in close collaboration with some of the projects that were led or worked alongside the university, so like specific. And this gives an overview of how these buildings will play a role in the future of the world's energy supply.
The world faces an energy challenge. How do we meet growing demand for electricity and heat in a way that is low carbon, affordable and reliable? Buildings account for about 40% of the world's carbon emissions. In the UK, they consume about 40% of all the energy produced. To solve the energy crisis, we need radical change in building design. Imagine if buildings could produce and store enough renewable energy to meet their own needs or more. Specific Innovation and Knowledge Centre at Swansea University is developing technologies that capture heat and electricity from the sun and store it in a building until it is needed. Specific staff develop technology from the lab to full building scale. They've designed 2 demonstration buildings to show how technologies can be integrated into a building to generate, store and release heat and electricity in one system. In its first year, the active classroom generated 1.5 times the energy it used. The excess goes to charge electric vehicles or to the local electricity network. To make a difference, we need many buildings like this. That's not only a technical challenge, but a political, social and economic one. The Active Building Centre will provide the evidence that regulators, policymakers and the construction industry need to transform construction in the UK. The new centre will support active building developments, analysing data from the people who live and work in them and their energy performance when connected with each other, with electric vehicles and the grid. This is a great opportunity for the UK, so imagine you're in a place where there is plenty of sunshine and no grid connection. Sunrise unites universities and industry from the UK and India. The project will work with local communities to build at least 5 demonstration buildings in rural India. It will develop efficient, low-cost solar technologies and lasting relationships that help both countries to promote low-carbon buildings. Together, Specific, the Active Building Centre, Sunrise and their partners are working to demonstrate how buildings can be designed differently, at scale, to reduce carbon emissions and to support change for the next generation.
Okay, so just to cover, to reiterate what was in that video, we see active buildings as an integral part in helping the UK and other countries, obviously, with its growing energy demands. Active buildings are able to generate, efficiently manage, store, share, and pass energy that is unused back into the grid. You can liken it to seeing a home or building as a mini power station. Active buildings are designed to maximize both physical and psychological comfort for occupants whilst being energy efficient, combined with using integrated technology and smart controls. And by reducing the demand of the building and installing local renewable energy generation, active buildings sort of free up energy to support the electrification of transportation and heating, as well as the wider energy network. So these buildings can not only power themselves, but they can also support the wider network as well. And in the case of low carbon active buildings, considerations are made from the get-go about how to minimize the carbon emissions. And this includes from initial material selection to the construction process and manufacturing methods, as well as operation of the building in terms of renewable energy utilization, electricity generation, operation emissions, and it also includes the disassembly or deconstruction process at the end of life as well. So what is an active building? We can break this down into 6 main principles. Firstly, we have building fabric and passive design. And I'll go through these in more detail in the next slides. But this is aiming to design buildings that use minimal energy to be needed for heating or cooling, so that energy bills are low. Next, we have energy efficient systems and monitoring, things like heating and ventilation and lighting smart systems. We also have active buildings will also incorporate on-site renewable energies and generate their own energy via things like solar PV, solar thermal, wind, and so on. And also energy storage. So this energy that's been generated locally can then be stored for when it needs to be used. And finally, electric vehicle integration. This enables energy to be shared with vehicles in a much more controlled way. and also buildings integrating with the energy grid, as mentioned, so we can manage their interaction with the wider energy networks. So again, another short video. I think this might be the last video actually. And this is an overview of an example building, a demonstrator building built by Specific at the Bay campus called the Active Classroom.
The Active Classroom is the UK's first energy positive classroom. Over the course of a year, it will generate more solar energy than it uses. The classroom is located at Swansea University's Bay campus, where construction was completed in October 2016, just 14 weeks after the steel screw pile foundations were installed. The building is used for teaching students as well as for meetings and workshops. It is a building for learning from, not just in. The steel roof has 16.2 kilowatt peak of integrated 6 photovoltaics. They are used to power the building directly and to charge 2 saltwater batteries. The batteries have a combined capacity of 40 kilowatt hours, enough to power the building for at least 2 days without top-up. Heating is provided by a solar thermal collector on the south-facing wall. Warm air is drawn into the building through the tiny perforations. On a sunny day, it can provide enough heat for the building even in the middle of winter. Heating is also provided by floor panels coated in an electrical resistive coating, which heats up when a low voltage is applied. Nearly all of these technologies are available on the market now. The innovation is in the way they work together. As our first complete building as a power station, the Active Classroom will be used to test and validate energy performance and to see how users experience and interact with the building.
Okay, so brilliant, absolutely brilliant building. Principles of active building design. So back to those principles that I mentioned earlier, these can actually be sort of grouped into 3 main parts or areas, and 3 purposes really of why they're important. Firstly, building fabric and passive design, as well as energy efficient systems, can be grouped into what's called reduce, and this is not only reducing the energy required to heat and run the building, but it's also optimizes the energy systems so that they're running efficiently and therefore reducing the operational energy. Next is optimize. So here we're able to optimize the renewable energy generation, for example. So building loads are met using these technologies, and as well as we can optimize the storage of these, so that this helps to reduce the issue with peak loads. And we've always got that backup there in the energy storage system, whether that's electrical or thermal. And then finally, having electric vehicle integration, as well as being able to manage the interaction with the grid, will give us much more control of the import or export of our energy. And this is actually a novel feature of active buildings, in that they can function as part of a decentralized power distribution system and actually manage their energy, as well as ensuring the energy is distributed appropriately to meet their needs. And if they've got excess, then we can sell some of this back to the grid as well. So let's go on to some of these principles now in a little bit more detail. Firstly, buildings should be designed in harmony with their site location and site conditions. They should have a high level of fabric efficiency, well insulated materials, and well insulated airtight construction as well, to ensure that the heat and the warmth that we're putting into the building stays and builds up, especially during the colder months. And also the insulation will help in the summer months to prevent overheating and things like that. Creating a comfortable environment for the occupants. The ideal then is that very little energy is actually needed for heating or cooling, and that the energy bills stay low. The starting point for an active building is an efficient building fabric and optimized passive design to reduce this operational energy. When we're thinking about the design of these buildings, we should be thinking about ideally the orientation and massing, the fabric efficiency, the natural daylight and natural ventilation sort of options that are available. And they also, these will need to be considered as part of an integrated engineering and architectural design approach. The buildings or homes should be designed for occupant comfort and as well as low energy by following passive design principles, and then also considering low carbon technologies and energy systems where possible. Things like building massing, you may or may not have heard of that before, but this refers to the overall configuration of the building. Things like site size, geometry, topography, and configuration really in relation to adjacent streets or buildings and things like that, okay? An example of a site analysis diagram. Here we can see the building fabric with a passive design. And this illustrates some of the different types of environmental factors to consider. So let's have a look at that in more detail. We should consider really a passive and or an active solar energy. So we can try and ensure unshaded south-facing facades. You know, in that particular point there is quite self-explanatory. You often see solar panels on people's houses and they are facing the sun. That makes total sense to get the maximum amount of energy that can be generated from those cells. But there's other technologies which can use not indirect sunlight, and also gain energy in terms of solar thermal as well. So east and west facing surfaces, for example, can also be utilized. And they're not going to be as efficient, but if you already filled the south-facing facades, then you can also generate energy from some of the other sides as well. So we can undertake early modeling to predict the impacts of this sort of siting and orientation with anticipated user profiles as well. Things to consider and opportunities for green infrastructure around the building. We need to ideally try and reduce flood risk, include biodiversity, so we're actually contributing to the environment that these buildings are going to be in. Improve the health and well-being of occupants, and things like provide an attractive site, improve air quality, and also make use of passive cooling and shading. So you can see that here we have the sun. I'm not sure if you can see my cursor actually, but where you can see the sun's path around the building. We can do things like plant low-level deciduous vegetation for natural summer shade. And we can also put vegetation on another aspect of the building to prevent or to minimize the effects of noise or pollution, for example. So here we can see the deciduous vegetation in the summer, providing shade, natural shade, and helping to cool the building, therefore reducing the requirement for things like, you know, aircon or fans, you know, the cooling systems. And then in the winter, obviously the trees and the plants will lose their vegetation or their leaves, and this will allow then for the sun to penetrate and heat up the building. So we've got passive solar heating helping, therefore we don't need the heating on as much in the building. So it's things like that which can contribute to the passive design. Number 2, energy efficient systems with smart control strategies should be employed to further minimize the energy used for heating, ventilation, cooling, and lighting. It's not just a case of turn the heating on and then turn it off, well, just leave it on for an unknown length of time. We're building into the system techniques to capture that data and also to improve on, to improve the efficiency and maximize the amount of energy that we're putting into the amount of energy that we're, in terms of heat and ventilation, that we're experiencing as occupants. Data capture is extremely important here via inbuilt monitoring technologies, and enables optimization and refinement of these control strategies. Regulated loads are further minimized using these intelligently controlled energy efficient systems. Ongoing data capture then will enable analysis and insight into feedback into a feedback loop into the active building design process. We can predict energy loads using models and then base this on the building fabric and passive design attributes. And then the building's internal gains must be recognized from solar, occupants, activities, and equipment. And all this can feed back into the system. Some key design considerations include the adaptability of these systems. For example, if you want to incorporate a new technology years down the line, or something needs to change within the system, we need to have a highly adaptable and easy to adapt system so to help with that. Controls, simple sort of controls that the majority of users can use. Heating, ventilation, cooling, lighting, and water considerations, and combining these systems for maximum efficiency. Thirdly, on-site renewable energy generation. This should be incorporated to supply the buildings with their own low-carbon source of energy. This can include things like solar PV, solar thermal, wind, water. If you've got, say, for example, a water source nearby, then we could look at hydro energy, air source or ground source heat pumps as well. And like I mentioned, any excess energy can be integrated with the grid. Where practical, these building loads are met using these renewables. And these should be selected holistically and taking into account the site conditions and the individual building load profiles for that building. And as an example here of some of those technologies and where you might sort of incorporate them into the building. Wind turbine, again, is great for some applications, but I probably wouldn't be too happy if my neighbours put a wind turbine in their garden. So there's things to think about with each individual building or project. What type of technology should be used and can be used as well. So again, yeah, this comes into technology selection. These decisions on which technology to use and the size of generation system will be affected, sorry, by things like planning constraints, predicted energy consumption, site conditions, the building type, aesthetics, things like cost requirements, clients' requirements, the cost of those technologies, as well as maintenance requirements and the available area that you can use for energy generation. And for example, if using building integrated photovoltaics, the roof dimensions may be determined by the size of the PV modules. So those things need to be thought about in the design process stage. Energy storage. Both thermal and energy storage are included to maximize the use of renewable energy. Adopting measures such as batteries to store energy help mitigate the peak demand and reduce the requirement to oversize systems will enable a greater control of energy consumption. In addition to reducing peak loads and preventing oversizing of the plant or the home, the inclusion of electrical and thermal storage allows interaction with microgrids as well as the wider national energy network. It gives greater control basically of where and when to use that energy. Electrical storage is probably essential for most applications to enable optimum use of electricity provided by the renewable energy generating technologies and also the grid. The most widely used form of electrical storage is batteries. This enables us to manage any lulls in energy generation. It allows building owners to choose when to use or export their energy. Reduces the pressure on the grid, especially during high demand, and allows export of both spare power being generated at a point in time. Okay. Thermal storage, also very useful and probably essential for most buildings as well. Thermal storage is used to store renewable heat as thermal energy. And this is generated during the summer months for use in the winter, or to capture waste heat if you're talking about an industrial project. So from industrial processes, we can capture this waste heat and use it then when and where it's required. It's a key technology to decarbonize heat in the UK. And for the true benefits of a solar heating system, the storing of heat generated should be until the heat is ready to be used. That makes sense. So to help with this, there are three main different types of storage. You can see there in this table: sensible, latent, and thermochemical. Each different type will have a different length of time that you can store this energy for. And having the right one or a combination of the right ones for what you need it for your unique building project is critical, really, to maximize the solar heating storage system. Sensible is more short-term in a matter of days, and you can see the energy density as well is smaller, and it goes up as you go to latent. And finally, thermochemical, which you can store interseasonally. And this is usually, for example, through a thermochemical process by passing warm air over a salt in the matrix. So that's just one example of how this energy could be stored long-term, for example, from the summer and then used into the winter. Electric vehicle integration should be incorporated into these active buildings as well. This again enables energy to be shared with the vehicles in a controlled way. It's it's having an extra battery there on the side of your building, so you can utilize that as you wish. Some factors to consider when designing for electric vehicles include EV charging requirements should be determined before sizing the energy generation and energy storage systems. You should be able to identify the power requirements in order to inform the electrical design. And also the location of chargers in relation to the building and the electrical connections. So all this needs to be thought about, including the site layout as well. And we can identify the types and quantities of EVs that charging facilities are required for. Things like electric cars, but not just that, we've got electric motorcycles or electric vans and more pedestrianized transport like electric bicycles and electric scooters. So these could be in a bike shelter, which could have their own integrated, as you can see from the schematic there, own integrated PV roof to provide the energy directly to the modes of transport. And we can also get smart chargers, which can shift the time of day when an EV charges, or to modulate the rate of charge at different times. This allows the building owner to change the speed of charging, or in fact delay the onset of charging based on variables such as demand or carbon intensity of the grid at that time, or as a response to the price, to the cost of that energy. So yeah, it just allows for much better management of the energy. Finally, to finish these 6 principles, in addition to controlling the energy use within a building, as well as with any vehicles that we may have, control strategies and energy storage enables active buildings to manage their interaction with, say, the national grid, controlling when energy is imported or exported. This helps stabilize and reduce pressure on the grid from otherwise uncontrolled import and export, which we've probably all noticed recently with, well, no, this seems like a year ago now, isn't it, or two, where our bills all went up. But due to this uncontrolled import and export of energy, which is, again, critical to manage in a decarbonized society. Characteristics of an electrical demand management strategy include things like reducing the building's demand on the grid, equipping the BMS, or the building management system, with the ability to forewarn occupants of likely load peaks in advance. So if you do very similar processes at certain times of day or certain times a month, then we can tell a system to give us a warning of that, and we can account for that then. We have things like enabling flexibility and reducing peak loads, therefore reducing the cost and eases pressure on the grid. This actually can create then business models which will allow for value creation. We have something called demand side response, or DSR, which provides an opportunity for active buildings to play a role in the operation of the electricity grid by reducing or shifting their usage during peak periods in response to time-based rates or other forms of financial incentives. This is already happening really with Octopus Energy, as just an example, where they tell you to hold off on doing your washing in the machine until the night, and we'll pay you some cash towards that. So this enables dynamic energy pricing as well as reducing the grid stress. And other things like predictive controls and self-learning optimization. This can be based on price or carbon intensity, and also weather forecasting as well can help to decide on what we're doing with our energy at that specific time. Okay. So yeah, really important aspect of active buildings. I wanted to show you some case studies now, which have been real demonstrators, which have been built, majority in South Wales, and by mostly by Specific, who have kindly let me use all their resources in order to build the course and to build this presentation as well. So Specific have designed and made a variety of active buildings to date, a selection of which can be seen here. They've made a range of different building types and sizes, and they've used a diverse selection of new technologies within this building. When you get sent the slide pack, there'll be links to all of these demonstrator buildings, so you can read the case studies on each one. I'll go through some of these in a little bit more detail now. So first up, the active classroom. We've already seen that short video on the active classroom. This was initially built, when it was initially built, the energy storage system consisted of these novel aqueous hybrid ion batteries, which we saw in the video. These have been illustrated here. These have since been removed, and a different type of battery system, which can be seen on the slide now. Flow batteries have been installed. This ability to trial different battery energy systems and also different technology systems in real world conditions is one of the main purposes and benefits of the buildings demonstrators. It's to study and test and learn how best to go about these active buildings and the technologies that are being developed concurrently, and then to share those learnings as well to improve for the next one. This was constructed in 2016 and incorporates solar PV, solar thermal, battery storage, novel heating systems, and also a new form of construction as well. It's also enabled a test base. It's been a test base for low carbon technologies, and also a pilot study with measurable.energy to test a new real-time power monitoring system. And then actually the next phase for this building is deconstruction, because even though it doesn't need to be deconstructed per se, it's going to be a very useful project and very useful activity to do, to see exactly what we can reuse, what can we recycle, and how high, how much of it can we actually save from landfill. And let's see what we go to. Okay, so we're going to the next one, which is, the next one, just checking, is the active office.
The Active Office is the latest building in Specific's full-scale demonstration programme, which aims to test and prove the active buildings concept in a range of building uses. Buildings currently account for around 40% of UK energy consumption. So in order to help tackle this problem, the office is designed to generate more energy than it uses over an annual cycle. A range of commercially available innovative technologies enable the building to generate, store and release solar energy in one integrated system. These include the first commercial installation of BIPVCo's photovoltaic roof on a curved profile, which uses thin film solar cells to convert sunlight to electricity, and photovoltaic thermal tubes by Naked Energy on the south-facing wall, which are capable of generating both heat and electricity from the sun in one system. The energy generation capabilities are not only used to reduce emissions from the building, but are also used to reduce emissions of vehicles. During the first 4 months of operation, the building exported 1 megawatt-hour of electricity to electric vehicles. This is equivalent to approximately 3,500 miles saved for the Swansea University EV fleet. The Active Office is right next to the Active Classroom, which was really successful in proving the active buildings concept by generating 1.5 times the energy it consumed over an annual cycle.
So the Active Office is sponsored by both Cisco and Tata Steel. Tata Steel provided the products on the vertical cladding and they form the basis of the BIPVCo product on the roof. The Cisco network architecture underpins the communications and data collection for the building, enabling us to analyse and display the building performance and activity in a way that's both visually clear and informative. Using this information and data, we can plan how the building will use the available renewable energy. In the last year, the building has consumed approximately 26 megawatt hours. That's about 1/3 of the estimated consumption of a typical building of this size and type. The total generation is expected to be approximately 24 megawatt hours, and we're currently working on further optimising the systems to achieve the parity between generation and consumption over the annual cycle.
Our active buildings are examples of how buildings can operate without negatively impacting on the mains grid network. If every new building was considered a part of the energy system, in the way that the office and the classroom are, there will be a significant reduction in stress on the existing energy network infrastructure. This paves the way to transforming both the construction and energy industry.
Okay, thank you to Specific for providing that video. So yeah, I think we've covered it, covered the Active Office really in that video. Incorporated again a wide variety of new technologies, and importantly, the data collection and monitoring system, as Justin said, there was incorporated and also then displayed that back to the users to show them what the energy they were using at that time. So it also puts some ownership on the occupants as well of the users of the buildings. This again is just a snapshot of some of that data that's being collected and monitored at a set time on a particular date. I'm not going to go through it. I have got some notes, but just looking at the time, so I'll move on to some other data. This again is showing. So we have the red line here is the consumption data, and the green line is the generation data of the active office. This was from March 2019 to March 2020. And we can see that if we look at the data in a bit more detail, we can see that the consumption was actually 2.4 megawatts watt hours greater than the generation. But the majority of the energy here in that period was indeed captured, self-generated by the building, which is obviously brilliant and obviously a massive cost saving as well. Again, I'm not going to go through these graphs in too much detail, but it just gives you a snapshot of some of the data that can be gathered from these buildings and what we can learn from them. So we can take things like primary energy consumption and look at ways where further reductions can be possible. If say, for example, the lighting was taking up far too much of the energy consumption, then we can look at ways of reducing that, whether it's improving the technology or the bit of training with the occupants, things like that. We can also understand the carbon impact of the batteries, and we can optimize that further due to with battery imports and exports controlled by carbon intensity. So if cost isn't too much of an issue, then we can use carbon intensity as a driver for when we import and export energy. And we can also work out things like actual carbon in use as well. We can control the methodology, and we can also select, so the system then can recommend the lowest carbon energy source. Again, data monitoring and optimization is covered in the main course, online course that we have. So just to briefly cover some of the other demonstrator buildings that have been made or worked on in close collaboration with specific at Swansea University. We have something called the Shed Solar Heat Energy Demonstrator. This is obviously, as you can see from the pictures, a very large industrial size unit based in Port Talbot and very difficult to heat. And it was formerly heated by a gas-fired boiler. But since this system was installed, which uses the heat storage and a solar storage system, so the solar energy heats these materials. Sorry, let me see what else is there. So yeah, it heats these materials that can be seen here, the heat storage material, and then it's like a salt material. I can't remember the exact chemical formula, but then that's then stored in the heat storage system, and it's only needed then when it's only used when it's required. So since 2011, this has been heated without gas. Some data monitoring considerations, some things to consider when we are collecting and monitoring this data. Firstly, it's actually built into the regulations. So Part L, which I mentioned for Wales, this is actually built in, and it says the first line there says energy meters should be installed to allow effective monitoring of the performance of the newly installed fixed building services. So firstly, you've got to do it anyway, according to the regulations. And the way to do that, the different ways to consider when we're implementing it, the metering equipment, things like how far are we going to actually measure, how much detail do we want when we're measuring? We can either just cover the main distribution, so this is called a subboard level. We could split it into subboards, so we can have a lighting metering system, plant metering system or general, for example, and we could even go into the sub-circuit, right down to appliance and equipment level as well. So that's something that needs to be decided on. We've also got how that system is going to communicate, on what media it's going to use, whether it's going to be wired or wireless, via the internet or via different methods. And then how that's going to be analyzed. So is it going to be more like manual data extraction and then a team of people working on that? Or you can employ something like an energy management system or an EMS to do that for you. Specific and Swansea University, the team have been sharing their learnings, not just developing projects in the local area, but they've been, for this one, this is in close collaboration with Specific to deliver this community building in a rural village in India. Even though the village is connected to the grid, the electricity supply is often unreliable and of course expensive because they haven't got any other option. So Specific helped to design and build this building in order to generate, store and release its own electricity. So that was a great success, and the community have been able to use this building for basic things, really, like charging phones and devices and heating as well. So, and lighting, of course. And I'm not going to go through each and every one in that much detail, but again, this is across Hands East is a large mixed use development with industrial and office spaces. Again, the challenges encountered here by Specific were working with a lot of commercial designers and contractors, which means their influence was limited. And but nevertheless, it's projects that Specific have contributed to and shared their learnings about what they've learned making their buildings on the campus. Swansea University have actually worked closely with Specific as well on a separate project, which was retrofitting of low carbon technologies onto a teaching facility, whether it was an oversight or whether it was just not incorporated, not needed, and then the space was available. So they added on this facility, which gives photovoltaics on the roof, as well as the battery energy storage systems as well. Microgrid control, so we can control that energy back and forth between where it's required. Okay, let's go to impacts. So some of the social impacts that we're starting to see from active buildings: improved health and well-being. So the air quality can be better. We can have better and improved natural lighting and comfort. We can have acoustic comfort as well. Hopefully, if everything goes well, we'd have reduced energy costs, lower utility bills, importantly, energy independence as well. Creation, of course, of green jobs and a skilled workforce. And also we could start to see perhaps urban green spaces and reduction of urban heat islands if we're incorporating the sort of vegetation into our designs as well. And social equity and access. So we may be able to incorporate these into affordable housing where the bills are low and well insulated as well. And also social awareness and engagement of these types of technologies and climate change and everything. So yeah, hopefully they would be very impactful. Of course, the environmental impacts, if we're reducing our greenhouse gas emissions, then like I said at the start, up to 40% of emissions, up to 30% of carbon emissions were due to buildings. So a massive sort of potential of reducing those emissions. We can manage our water, for example, much more efficiently, and our material and waste consumption leading to a more circular economy, as well as green spaces and climate resilience and the adaptability to climate change, as well as the passive design elements. So rather than burning these fossil fuels and having an impact on the earth, we could just be much more passive and use the energy that's given to us almost. We can generate our own energy from that. So just to summarize, Specific and Swansea University have designed and built a variety of active buildings over the last decade. They've installed and integrated innovative low carbon building technologies into these buildings. and they have been able to test these new emerging technologies under real-world conditions. These structures are designed to reduce their carbon footprint by minimizing energy consumption, using renewable energy sources, and incorporating smart technologies that manage energy efficiently. And like I've mentioned, active buildings can offer significant social and environmental impacts, as well as aligning with the global growing trend of sustainable development and going towards net zero. Specific have also developed an active building toolkit. This can be found on Google with the link below. Extremely useful resource, and further reading as well possible there. Alternatively, or as well as, we've got a young person's guide to active buildings. This is just an alternative format, engaging infographics, designed to appeal to the next generation of engineers, which is also very useful to have a read through. Again, the link is there on the slide. And they also, via the website specific, they've got further case studies into industrially relevant research in materials or testing of a performance of a site and quality studies as well. Just to finish and conclude, I would like to highlight this quote. This was originally by Ian Campbell, Executive Chair of Innovate UK in 2018. He said that it was difficult to overstate the potential of developing a building that powers itself. And this seems even more relevant now, signifying the critical role that low carbon active buildings will play, they're already playing now and in the future, in order for us to meet our net zero targets, but probably more importantly, or just as importantly, to improve our energy security.